Hi, good afternoon and welcome. My name is Grant Wilcox. I'm from the Program Management Office with TriQuint Semiconductor, and I'm here to talk to you about the state of GaN development, both in process technologies as well as products. So really, what is GaN? What does it bring to the table? Bandwidth. We're producing products much higher bandwidth than we did for gas and achieving much higher power and PAE targets over that bandwidth. More power. That's really what GaN is bringing to the table for the past several years is power. And that's how everybody sees GaN is higher power density. We've been supporting EW and radar as well as communication markets with increased power products only available through GaN technology. It brings to the table higher efficiencies. GaN really separates itself from gallium arsenide in terms of efficiency when you go higher in frequency as well as broader band. What we're achieving broadband with GaN is twice as efficient as what we achieved in gallium arsenide. Same thing as you go into KU band, even to KA band, the efficiency levels that you can achieve with GaN are twice as that, if not more, than what we were able to achieve in gallium arsenide. Higher temperature. Now with the added power, different system level designs will either shrink the die to get the same amount of power over the same form factor, or they'll make the die bigger to get even more power. But in either case, what the system designers will have to design for is thermal management. So how do you manage 5 times the power dissipation out of GaN than you did for gas? The good thing with GaN with silicon carbide, which I'll show in a later slide, is the reliability for silicon carbide is much more than we ever achieved for gallium arsenide over temperature. So where 1,000,000 hours for gallium arsenide was 150 degrees C junction, we can achieve 1,000,000 hours with GaN at 200 degrees C junction, if not higher. And then advanced R&D, I'll get into that in a few slides, where we're basically going higher in frequency, higher efficiencies, thermal management, and I'll get into that in the next slide or two. So what is TriQuint bringing to the table as far as process development? As I said, the market really, or the supply of GaN, really focused on 6 gigahertz and below. So there's a lot of half-micron technologies out there to support the 6 gigahertz opportunities and below. What TriQuint brought to the table was the quarter-micron GaN that had operation up through 18 gigahertz. And then we developed that through our DARPA program, phase 2 and phase 3 of the DARPA program. We're supporting foundry as well as products. We're supporting the same 6 gigahertz and below products with our quarter-micron process. That gives you the higher efficiency, higher gain than the competing half-micron technologies. But it also allows the customer base to achieve world-class performance up through X band as well as KE band using the quarter-micron. To attack the KA band market, we're developing a 0.15 micron technology. It won't only support the KA band power, but also wideband, low noise figure LNAs. So we'll be producing a variety of products using the 0.15 across frequency, across power levels, and world-class LNAs with it as well. And then even extending the frequency coverage up through W band, which we have a contract for, as well as up through 500 gigahertz for high-speed logic applications. So I'll get into that in the next slide. So as I mentioned, TriQuint's leading the technology push for GaN. And we're doing that in conjunction with government contracts as well. The government is still focused very heavily on GaN maturity, the GaN technology, the performance they can bring not only to support the low frequency applications, but the high frequency opportunities that it sees coming down the road. As I said, and TriQuint is the leading provider of that technology, as you can see in this list of government-sponsored programs. Title III, for example, is basically a manufacturing program brought to us by Air Force Research Labs. And that's really to expedite the maturity of GaN, the existing GaN that we have today. As I said, the government's put a lot of money into gallium nitride. It wants to use that technology in its larger systems. So it needs the supply base to expedite their learning curve, so to speak. So what Title III does is basically from a yield standpoint, variation, tightening, things of that nature, to get the supply base up to the point that they want to be able to support high volume production programs. Thermal management that I mentioned before is a key component in any system design using GaN. The NGATT program through DARPA stands for Near Junction Thermal Temperature. That's really how to better manage the high power dissipations that you see with gallium nitride. And basically what this is a GaN on diamond activity. Diamond is a very good thermal conductor, so we're investigating the ability to use diamond as a substrate. The DARPA Next program is basically a high-speed logic type application. There's been several phases. We just finished phase 2, which allowed greater than 200 gigahertz of operation. Phase 3 takes it up to 500 gigahertz of operation, and that's to support the high-speed logic applications. MPC stands for microscale power conversion, and the focus there is switch-based amplifiers for high efficiency, just improving the efficiency of the gallium nitride amplifiers. And then W-band LNAs, basically higher sensitivity up at W-band, and they're just primarily using an ED-based technology. So why GaN? Greater efficiency, the system simplicity. I guess the simplicity increases, reduced BOMs, greater efficiencies from lack of combining versus gallium arsenide. As you can see here, you have 4 gallium arsenide 6.5 watt KU band chips. You can achieve the same power performance in 1 GaN chip, and the improved efficiencies through lack of combining moving to the GaN. This gets you that 2, sometimes 3 times in efficiency using the GaN, because you don't have the combining losses that you have with gallium arsenide. Anyway, that's a pretty good pictorial of from a system standpoint. That if you don't have to if you can only use 1 chip versus combining 4 or more in some cases. We have some customers that are combining 16 to even up to 32 gallium arsenide chips. Some of the GaN chips that we're developing can solve that or can support that same application with 1 or 2 chips. So why GaN? As I mentioned before, higher bandwidth, lower combining losses, improving the efficiencies, the higher temperature operation. To handle the higher power dissipation, we can run junction temperatures 200, 225 and still maintain the million-hour lifetime. And then efficiency, really broadband, high frequency is where the benefit comes in. There's benefit definitely in the lower frequencies. I don't want to give that impression, but it starts separating itself significantly as you go broadband and high frequency. So bandwidth, efficiency, and power. And this is where I said the focus has been on power, but you'll see in coming product releases, you'll see LNAs, switches, possibly limiters. We're really expanding what the product portfolio that gallium nitride can support. And then the temperature. So why GaN on silicon carbide? Of course, there's comparison to gas, there's comparison to GaN on silicon, which there's some suppliers out there that just use silicon for their substrate. But it's really from a thermal standpoint. You can see here the thermal conductivity as you go from gallium arsenide to GaN on silicon carbide increases 6-fold. That reduces your channel temperature, then your reliability goes up. So with the high power densities, high power dissipations associated with gallium nitride, silicon carbide to date is the preferred choice for substrate. As I mentioned earlier, our NJTT program is investigating GaN on diamond as a next step in that. So from a standard product standpoint, with the maturing of the GaN process, our product portfolio is also maturing. This is a quick snapshot of the families that we're developing. We have transistors, both bare die and in package form, GaN amplifiers, both wideband and narrowband, and GaN switches. We're achieving power handling levels that gallium arsenide cannot achieve, and much smaller form factors, much smaller current draw than a pin switch would achieve, for example. But I do have more detail on those families. So on the power GaN transistors, so transistors really allow customers quicker to market, a lot more flexibility in their designs, because you're basically designing to your specific specifications. But what GaN brings to the table, it gives you a quick access to the power levels that GaN achieves, the broadband that you can achieve, and then achieving the increased efficiencies over that broadband. Target markets, again, a lot of them are general purpose, so both defense, commercial, instrumentation, basically the broad market is using the GaN transistors today. As you can see, the package transistors are general purpose packages, and product development going forward will just increase that power chain. High power amplifiers, this is where a lot of the focus has been on product development over the past couple of years, both broadband and wideband. This 2 to 18 part is world class. There's no competition to this product over that broadband that you see there. That was developed through our DARPA program because we were developing the wideband, the high frequency quarter micron technology. Again, world class performance at 10 watts over that band. It also achieves about 20% efficiency over that band as well. 2.5 to 6, lots supporting IED jammer type applications. Again, best in class. 13 to 15 gigahertz, targeting the VSAT market, and 14 to 16 targeting some mini CDL, common data link applications. Again, these are world class. There's no competition. That's what GaN brings to the table. What we were able to achieve with gallium arsenide is nowhere near what we can achieve with GaN at these frequencies that I'm showing here. So again, these are 20 watt levels, achieving efficiencies 25 to 30%, where the gallium arsenide, you're looking at a 6 watt level with efficiencies around 15 or 20%. So really step function improvement in performance using gallium nitride with the power amplifier. So from the target markets, EW has been a big benefactor of gallium nitride early on, less than 6 gigahertz, saturated power, just blast as much power as you can out there. GaN was perfect for that. Now we're moving more into more applications in X band and KU band. Customers are caring about linearity a little bit more. Maybe efficiency over power in some cases. So the product portfolio is growing from those customer demands. High power switches. So away from the amplifiers for a second, what GaN brings to the switch portfolio is power levels, power handling levels that gallium arsenide couldn't achieve in the past. So TriQuint is bringing to the table currently 3 switches over different frequencies and associated power levels. So we have a DC to 6 achieving 40 watts power handling, a DC to 12 at 20 watts, and a DC to 18 at 10 watts. The benefits here from GaN, again, the power handling, but the small control current that you see is microamps versus milliamps, if not amps, for pin switches, as well as the form factors. These are very small compared to what you would normally see for a pin switch. So again, TriQuint's offered these for the past 6 months to a year, and the product portfolio for switches will continue to grow, either in frequency, power handling, if not both. So those are the products that are available today. What's going to be tomorrow or next year? What's GaN bringing to the table? Because as I said, a lot of the customers are saying, okay, we have the power amplifiers, what else can you do with it? Low noise amplifiers will probably be the next frontier for GaN product development. It brings, the main item, benefit it brings is survivability. We'll be doing some more research, some more testing throughout the next several months. But right now, GaN brings orders of magnitude improvement over survivability over gallium arsenide. So you hit the, an LNA with power. That's why you have the limiter in the chain to protect the LNA. But if you have a GaN LNA, it can handle, well, the early data has shown 6, 7, 8 times more power input than what a gallium arsenide LNA can handle. So that could potentially eliminate the limiter from the receive chain and ultimately, improving your overall receive chain noise figure. So that's where a lot of the benefit is for the low noise amplifiers. But again, our 0.15 process that we're developing now is achieving as good or better noise figure that our gallium arsenide 0.15 process, which was world class. So really, we're real excited by the LNA potential for gallium nitride. High frequency. Again, we had the power levels up to KU band. The next frequency point where there's a lot of customer interest is KA band, both on the commercial side with VSAT as well as military radar and missiles and things of that nature. So the 0.15 process will give us the KA band power, and also give us the noise figure performance across that entire band up through KA band. Then high efficiency, as I mentioned, our MPC program is targeting switch-based amplifiers. That's really targeting the high, achieving higher efficiency. We're doing a lot of work right now on X-band efficiency levels. So this is where the switch-based amplifiers can really benefit. And then controls, getting away from the amplifiers again. We've seen what they can do for switches. We'll continue that progress on the switches. But limiters, what can GaN bring to the table for limiters? We are investigating that right now, as well as mixers. Mixers. There's a lot of questions on what GaN can bring to the table for mixers. Well, we don't really know yet. We haven't tried it, but in theory, the higher compression point, higher linearity, the dynamic range ultimately will improve. So those are things that we need to look at and investigate. So in summary, TriQuint's been a GaN R&D innovator since 1999 when we started working at university levels and the materials. We've grown through that into the DARPA Phase 2 and Phase 3 programs and the follow-on list of government-sponsored contracts that I listed earlier. So we're continuing to lead the GaN technology growth. It's a maturing technology, both from a natural timing of it, a natural progression of production volume, as well as the government Title III programs, which is basically expediting that maturity. TriQuint is definitely pushing that along and to help the customer base from a high volume production standpoint. It is having a broader appeal across markets. The primary focus was military for the past several years. The commercial guys over the past 6 months to a year is starting to gain a little interest, both base station, cable TV, point-to-point, to name a few, are starting to engage with gallium nitride technology and seeing how it can impact their system designs. And as you mentioned, and as I showed, TriQuint offers a wide variety of GaN solutions, both from a product standpoint, FETs, transistors, mimics, both bare die and package, as well as foundry services. We offer the foundry, so customers want to do their own designs, the flexibility to do that, we offer that service as well. And then TriQuint is developing new processes, new products to really dictate what GaN brings to the table, not 6 months from now, not a year from now, but even beyond that. So as I said, with the government R&D activity, the product development, and the process enhancements that we're working on, TriQuint will continue to lead the GaN technology for years to come. So thank you. Any questions?
I got one, Brad.
Sure.
You mentioned 0.15 micron, you're investigating the LNA performance. Any idea how your quarter micron is?
The quarter micron showed that equivalent performance that our quarter micron gas has. So, and I'd say as good, if not better, on the data we've seen. So we've had some We haven't done any designs ourselves or full up LNA designs. We've done some unit cell characterization, but we've had some foundry customers do LNA designs, and the performance was quite impressive. So we're excited about it.
Wonderful. Thank you.
Hi, my name is Tim Vaughan, and I work with Richardson RFPD in strategic marketing. I hope you've seen that TriQuint will be a fantastic partner for any of your GaN requirements going forward. They've been involved with GaN development since DARPA first started funding it, and they continue to innovate with new processes and new products coming out on a regular basis. So I certainly hope you will consider TriQuint and Richardson RFPD for all your future GaN product needs.